Let's talk about how to find roots of complex numbers. Now, to start off with this, we're going to start off with a very simple complex number, just 8. That's one of the simplest complex numbers you can get. We don't have any roots in there. We don't have 2 plus root 3i. We don't have any i's in there even. We're going to start you off pretty simple here. And we want to find the cube root of 8. Now, you already know one of those. One of the cube roots of 8 is 2. However, what I'd like to do real quick is some algebra here. So let's remember some 1050 skills. Let's cube both sides of this to get x cubed equals 8. And then bring everything to one side. And we get a polynomial. X cubed minus 8 equals 0. Now, if you remember from the fundamental theorem of algebra in 1050, we talked about a polynomial should have as many roots or zeros as the degree of the polynomial. This is a degree 3. Degree is the biggest exponent, x cubed. So because it's degree 3, I should have 3 roots. Now, like we mentioned before, we know that x equals 2 is one of those roots. So if we know one of the cube roots of 8, I can use that to find the other 2 using synthetic division. So we take the one root we know and we do our synthetic division. Hopefully you remember this. Multiply and add, multiply and add. So this is remainder 0, no x's, x to the first x squared. So that means x minus 2 and x squared plus 2x plus 4 is how we would start to factor x cubed minus 8. Here's the one root I do know. This will give me the other 2 roots. So if I take x squared plus 2x plus 4 and try to factor that, you'll notice pretty quickly there's nothing that multiplies to 4 and adds to 2. This is a quadratic formula problem. So I take negative b plus or minus square root of b squared minus 4ac all over 2a. And we start to simplify that. We get a negative in this root, which tells us the other 2 roots are imaginary. So we have negative 2 plus or minus. If I simplify the square root of negative 12, it gives me 2i root 3, which then I can divide both of those. Get negative 2 over 2 plus or minus 2i root 3 over 2, which is negative 1. Plus or minus I root 3. So that tells me the cube roots of 8 are 2. The one that I knew, when you cube root 8 in your calculator, you get 2. Negative 1 plus I root 3. And negative 1 minus I root 3. And like we said, we should always get as many roots as we have is the power or the degree. So because this is cube roots, I should get 3 answers. In this case, I get 1 real answer and 2 imaginary or complex answers. So this is how you would have solved it back in 1050, solving this algebraically. And that works as long as the numbers you're dealing with are fairly simple. But that's about to change really quickly. I'm going to give you things like find the square roots of this, or find the cube roots of this. You can't really do that algebraically like we did with the 8. So we need to come up with a polar form rule that lets us come up with these same exact answers, but using a polar form, so then we can use that rule for more and more complex problems. So let's go back to finding the cube roots of 8 but we're going to find this out using polar form. So there's my complex number, 8 plus 0i. I want to find the cube roots of that. So first thing I want you to do is find the modulus and the argument and write this in polar form. Modulus, cis, argument. Pause the video, just try that part, and then come back to check your work. Let's check your work first. Found the modulus is 8 and the argument or the theta is 0. Now, so that means that z would also be written as 8 cis 0. Now bear with me for just a moment. I am going to take this argument and change it to if I asked you to find all arguments. We know that 0 is not the only theta that gives me this point. I could add 2 pi k and get to the same theta every time. So I'm going to write that in. To find all my thetas, I would add 2 pi k, and that gives me all answers, all thetas that work. Now, here's what I did. I want to find the cube roots. So I have x cubed is going to go with my 8. And I'm going to do this 3 alpha. And I'm going to line up my thetas. So I have x cubed equals 8 and 3 alpha equals 0 plus 2 pi k. And actually, let's highlight all of this. Okay, let's solve. So to solve for x, I cube root both sides, and this is essentially giving me the modulus of x. Basically, the modulus of my cube roots. Then for my theta, which in this case I called alpha, I get 0 divided by 3 is 0, plus 2 pi thirds k. This is the argument of my cube roots. Now, remember we learned that if it's a cube root, we should have 3 answers. That we know. So my first answer is going to have the modulus of x, cis, my first argument. My second answer is going to have the modulus of x, cis, my second argument, which is adding 2 pi thirds, because that's how much we're adding each time. And my third answer will be the same modulus, but we're going to add 2 pi thirds again. So let's figure all these out. I know my modulus is 2, so this one is 2 cis 0. This one is 2 cis 2 pi thirds. And this one is 2 cis 4 pi thirds. I can write this out all the way. And use my unit circle to solve these. So cosine of 0 is 1. Sine of 0 is 0. So that gives me 2 plus 0i, which is just 2. Cosine of 2 pi thirds is negative 1/2. Sine of 2 pi thirds is root 3 over 2, which gives me negative 1 plus I root 3. And cosine of 4 pi thirds is negative 1/2. Sine of 4 pi thirds is negative root 3 over 2, which gives me negative 1 minus I root 3. Notice, same exact answers as if we had done it algebraically. That's what we got algebraically. Here's what we got with our polar form. Now, in this case, you might say, Mrs. Johnson, this algebraic process was way faster and simpler than doing all of this work. And you're right. But that's because the algebraic process was possible. I asked you to find the cube roots of 8. That was a really, really easy one to do. That was an easy number to find the cube roots of because you already knew one of the answers was 2. However, if I start to ask you to find, say, the square roots of negative 2 plus 2i root 3, you can't do that using this algebraic process. You have to use this polar form process. So, once again, the more complicated the numbers get, the easier the polar process becomes than the algebraic process. In summary, let's come down here and summarize how to take the roots of complex numbers. Here's our rule. We take the root of whatever the radius is, or the modulus, and then we divide the theta by that root number. So if it's cube root, divide theta by 3. If it's the fifth roots, divide theta by 5. And then we add 2 pi k over that same root number, just like we added 2 pi thirds in that last problem. And you keep adding this number for however many roots you've got. So if you have 5, if you're doing the fifth roots, you should end up with 5 answers, and you just keep adding 2 pi fifths to every single answer. If you're doing the square roots, then you're adding 2 pi divided by 2 until you get 2 answers. So that is our rule. Now, one last thing for this video before we practice this rule a couple times is I wanted to show you what these look like visually. If I take the cube roots of 8, which was these 3 answers, I had 2, negative 1 plus I root 3, negative 1 minus I root 3, and I graph them, I get this graph, which you'll notice is pretty artistic here. This is a graph, or sorry, I should say a circle. That's a very badly drawn circle. Forgive me for that. With a radius of 2 that is perfectly split into thirds. That is visually what finding the cube roots is. You have a specific radius and you're cutting it up into thirds. So if I wanted to find the fifth roots, I would be cutting a circle up into fifths. If I wanted to find the fourth roots, I would be cutting the circle up into fourths. And that is visually what is happening every time you find whatever roots of a number. So, understanding all of that, we now have a polar form rule that we can use for all examples. In the next video, let's actually do some examples.